Okay, today we're going to be talking about something called optimization, and essentially optimization is nothing more than you're basically trying to find the maximum or the minimum value of a particular quantity, such as the volume, surface area, or a variety of other different things. And so I'm going to give you a four-step process that you can use to optimize whatever it is that you're asked to optimize in that problem. The first one is you want to write the function to be minimized or maximized as a function of one or more variables. So let's say you're trying to maximize the area of a rectangle. Well, it would be a equals x times y. So that is what you're trying to minimize or maximize. And then if your function has more than one variable, then write some other equation that will relate the two variables together. There will always be another equation that you'll be able to have that will relate the two variables together. Third, by way of substitution, you're going to write the function to be minimized or maximized. You're going to rewrite the function you wrote in step one now as a function of one single variable. And then fourth, as we've been doing, you're going to take the derivative and find the critical points, make a number line, and you're going to use the first derivative test to determine whether it's a minimum or a maximum. And that is the process that you'll use to optimize various quantities. Let's see how this works on a few sample problems. Okay, example one, find two positive numbers such that the sum of the first number and 3 times the second number is 120, and the product of the numbers is a maximum. So I'm going to underline this. The product of the numbers is a maximum. So that last sentence tells us exactly what we are trying to maximize. So step one, I'm going to write the product as a function of two variables, x times y. This is what we're trying to ultimately maximize. Now it has two variables, so I need to write another another equation that will relate x with y. So that's where we use the first sentence. Find two positive numbers such that the sum of the first number, so we'll call x the first number, we'll say sum means plus, and then 3 times the second number, so 3y, equals 120. So now this is the function that relates the two variables. Now step 3, I'm going to rewrite my product function to be maximized as a function of one variable. So I'm going to solve this for x, because x is the easier variable to solve for. So I'll say x equals 120 minus 3y. I will take that and I will plug that in here for x. So now I'm going to write this in function notation. P of y equals x, but I'm not going to write x. I'm going to write 120 minus 3y times y. And so now I'm going to clean that up a little bit. So P of y equals 120y minus 3y squared. Now I want to find the maximum of this function. So I know that anytime I want to find the maximum of a function, I take the derivative. So P prime of y is going to be 120 minus 6y. I'm going to set that equal to 0. So 6y equals 120. So y equals 20. Now there's only one critical point here, so I don't need to do a number line. I can assume that it's going to be a maximum. So if y is 20, then I can now plug that back in here, and I can say, well, x plus 3 times 20, so x plus 3 times 20 is 120, so x plus 60 equals 120, so x equals 60, and y equals 20. Those are the two numbers that make this situation a maximum product. Example 2, a farmer plans to fence a field and then divide it into 3 equal parts. He has 200 meters of fencing. Find the dimensions of the field that will give the maximum area. All right, so let's see if we can draw our picture here. All right, we have some sort of rectangular field, and we're going to break it up into 3 equal parts. So that's going to be 1, and that's going to be 2. That doesn't look equal, but you get the point. All right, and so we need to find the maximum area. So let's underline what it is we're trying to maximize in this problem. Maximize area. So let's just call this x, and we'll call this whole side y. All right, so let's write our function to be maximized. Area is equal to x times y. All right. Now, we have 200 meters of fencing. So that's going to represent the perimeter and the middle parts. So we will say x plus x plus x plus x. So 4x is going to be the vertical strips of fencing plus 2y would be the horizontal. And that's all the fencing that he has. That's going to be 200. So now I have an equation that relates x with y. I can now plug and substitute in. So let's go ahead and work this out. 2y is equal to 200 minus 4x. Divide by 2, so y is equal to 100 minus 2x. Now I can go back and I can plug this in. So area is equal to x. I'm not going to write y. I'm going to write 100 minus 2x. And now I can write this in function notation because it's all one variable, so a of x. So a of x is equal to 100x minus 2x squared. Now I'm going to take the derivative to find the maximum of it. All right, now this is an upside down parabola, so we know that the only critical point that it's going to have is one of them. So a prime of x is equal to, the derivative of 100x is 100 minus 4x. We're going to set that equal to 0 when we get x equals 25. Go ahead and plug that back into here. So 4 times 25 is 100, so 100 plus 2y equals 200. 2y equals 100, y equals 50, piece of cake. Okay, example 3, we want to find the points on the graph of y equals 4 minus x squared that are closest to the point 0, 2. Justify your answer. So I've drawn this upside down parabola, 4 minus x squared, and I've put the point 0, 2 on the y-axis, and I've drawn an arbitrary point on the curve x comma y, over some x comma y. And what we want to do is we want to find the points on this curve where the distance from 0 to 2 to that point is a minimum distance, so the closest points. So what we want to do is we want to use this distance formula, and we want to find the minimum. All right, so let's see if we can do this. So the distance formula says y2 minus y1 squared plus x2 minus x1 squared square root, which is basically the Pythagorean theorem. So we're going to have y minus 2. So we're going to say distance equals the square root of y minus 2 squared plus x minus 0, which is just x squared. That's step 1. We have the distance in terms of both variables. Now we need to go in and we need to actually plug in what y is equal to so that we can get the distance in terms of x. So I'm going to write d of x now, which is going to be function notation. I'm going to replace y with 4 minus x squared. And 4 minus 2 is going to be 2, so this is going to end up being 2 minus x squared plus x squared. All right, we're going to FOIL this. So we're still not taking the derivative yet. We're going to FOIL this out. And that's going to give us 4 minus 4x squared plus x to the 4th. And then we have another plus x squared here. So d of x is going to be equal to, see if we can write it in descending power, so it'll be x to the 4th. And then a negative 4x squared and a positive 1 is a negative 3x squared plus 4. Now that is our distance. We need to find the minimum, so we need to take the derivative. So we'll finish that up here. So d prime is going to be, d prime of x is going to be, by way of chain rule, this is all to the half power. So I'm going to do 1/2 in front. I'm going to leave the inside function alone. I'm going to drop the power down to 1/2, and then I'm going to multiply by the derivative of the inside, which is 4x cubed minus 6x. That's my derivative. So now I'm going to rewrite this a little bit. I'm going to leave this on the top because it's not raised to any negative exponent. There's already a 2 on the bottom, and I'm going to move this down to the bottom. And so that's going to be the square root of x to the 4th minus 3x squared plus 4. This is our derivative. We know that critical points occur when the derivative equals 0 or when the derivative is undefined. Now, it may be a little bit different to figure out when this function here is going to be 0, but if we do what's called the discriminant, which is basically part of the quadratic formula, we'll see that it doesn't have any values. Let's go ahead and do b squared minus 4ac, which is a part of the quadratic formula. So let's do that. B squared is going to be negative 3 squared. That's going to be 9 minus 4. A is 1. C is 4. So basically we end up getting 9 minus 16, which is a negative 7. That is a negative number, so when you do the quadratic formula, you will not get real roots with that. So we know that there's not going to be any real solutions here. So then we can go ahead and set the top equal to 0. So 4x cubed minus 6x equals 0. We're going to factor out a 2x. That leaves us with a 2x squared minus 3 equals 0. So we get two answers, x equals 0, and x, actually we get three answers. X equals plus or minus square root of 3/2. All right, so we need to put those on our number line. And when you do, I'm not going to do it for the sake of time, but when you do that, you're going to find that there's going to be a minimum. They're going to see that there's going to be a minimum value at, oops, I didn't draw that right, at x equals root 3 over 2. So we're going to take that, we're going to plug it back into our function to find our y. All right, there's also going to be a minimum value at negative root 3 over 2. So both of those. So we're going to plug it back in, so we're going to get y equals 4 minus this squared. When you square a square root, that just goes away, so you're left with y is equal to 4 minus 3/2, which is 1.5, and that's going to give us 2.5. So there's going to be 2 points on this graph where the distance is at a minimum. And those 2 points are, running out of space, but they're going to be root 3 over 2 comma 2.5, and then negative root 3 over 2 comma 2.5. And those are the 2 points that are closest to 0, 2. Okay, this one's a little bit more difficult. A swimmer is 2 miles in the ocean. So here is your swimmer. All right, he's here. And he wishes to go to a town 3 miles down the coast. So 3 miles down the coast. And the swimmer is 2 miles from the coast. And the idea is the swimmer needs to swim to a point on the shore and then walk the rest of the way. And so he can swim at 2 miles per hour, and of course naturally he can walk faster at 4 miles per hour. So the question is, what point should he swim to along this coast that would minimize the time that it would take him to go from where he is directly to the town? Should he swim here and walk all the way there? Should he swim the whole way there? Should he swim to some point here and walk the rest of the way? That's what we need to figure out. So let's just call, well, let's tell you what, we're going to put a point here, and we're going to call this distance x, and we're going to call this distance here 3 minus x. Make sure that makes sense to you. This whole distance is 3. This is x, so we're going to call that 3 minus x. Now, 3 minus x represents the distance that he will have to walk. Now, the distance that he'll have to swim, we can get by using the Pythagorean theorem. So let's go ahead and do that. So x squared plus 2 squared is 4 is equal to the distance squared. So the distance is equal to the square root of x squared plus 4. So I'm going to go ahead and put that right there. Square root of x squared plus 4. Now we have to use this formula. Distance is equal to speed times time. Now if we divide both sides by speed, we can get a formula for time. So time is equal to distance divided by speed. All right, so what we want to write is we want to write a little equation. The total time that it's going to take him to get from where he is to the town is going to be broken up into the sum of 2 times. It's going to be his swimming time plus his walking time. So his swimming time can be written by his distance he has to swim divided by the speed he swims at. So the distance he has to swim is going to be the square root of x squared plus 4 divided by the speed he swims at, which is 2, plus the time walking. The time is the distance he has to walk, which is going to be 3 minus x, divided by his walking speed, which is 4. All right. So now that we have that, we want to find the, well, let's underline it. We want to find the minimum time. We want to say so that the time it takes him to be is a minimum. So therefore, we need to take the derivative of this. All right, so we're going to take the derivative. So we're going to say t prime of x is going to be, well, there's already a 1/2 there, so 1/2, but then I'm going to say 1/2, which comes from the chain rule, so 1/2, and then I'm going to leave the x squared plus 4 alone. I'm going to drop the power down to -1/2, and then I'm going to multiply by the derivative of x squared plus 4, which is 2x. Now here, I'm going to break this up into 3/4 minus 1/4 x. That way it's easier for me to take the derivative of this. That way, all I did was divide the 4 into both. So the derivative of 3/4 is just 0. It's a constant. The derivative of this is a linear, so that's going to be -1/4. Okay, so let's see what we have here. So 1/2 and 1/2 is going to be 1/4. And then I'm going to have a 2x on the top, and then a 4 times the square root of x squared plus 4. And that's going to be -1/4. And now I want to set that equal to 0. So we're continuing down here. The 2 and the 4 can be reduced to 1/2. So let's get rid of that. So we have x over 2 root x squared plus 4, and that's going to be equal to 1/4 when I move the 1/4 to the other side. So now I'm going to cross multiply, and so I get 4x equals 2 square root of x squared plus 4. And then I divide both sides by 2, so I'm going to get 2x is equal to square root of x squared plus 4. Now I need to get rid of the square root, so I need to square both sides. So don't forget to square the 2. That's going to be 4x squared. Let me write that a little bit better. 4x squared. And then the square of the square root goes away, so I'm left with just x squared plus 4. Move the x squared to the other side. I get 3x squared equals 4. And so x squared equals 4/3. So take the square root of both sides. I get x is equal to the square root of 4/3 plus or minus. We know that we can't have a negative distance, so it's just going to be square root of 4 is 2. I can take that out of the square root, and the square root of 3 does not. So that is the answer. All right, he needs to swim to a point that is 2 over root 3 down from the coast, and then he can walk the rest of the way. Example 5, you've been asked to design a 1-liter oil can shaped like a right circular cylinder. So a basic can. What dimensions will use the least material? So let's go ahead and underline. What are we trying to minimize? We're trying to minimize the material, the surface area. So we know that we need to minimize this equation. All right, so the volume of a cylinder we know is pi r squared h. The surface area is 2 pi r squared plus 2 pi r h. All right, so there's something that we need to know in this problem, and there's some units that we need to make sure that are consistent. A 1 liter is going to equal 1,000 centimeters cubed. So we need to make sure that we have our units consistent. So therefore, if it's 1 liter, I can plug that 1,000 in for the volume. That's going to be equal to pi r squared h. All right, and remember, we're trying to minimize the surface area, so we need to write the surface area in terms of only one variable. Well, the easier variable here to solve for is h, so I'm going to write this as 1,000 over pi r squared, and that's going to be h. So I'm going to take that h, I'm going to plug it into here, so I'm going to write my area in terms of r, so I can write it in function notation now, 2 pi r squared plus 2 pi r, and then h I'm going to replace as 1,000 over pi r squared. Okay, so now we're going to do some canceling out. We have a pi, we have one of the r's, can cancel with one of those r's down there, and so now we have area in terms of r is going to be 2 pi r squared, and then we have 2 times 1,000, which is 2,000 over r. Now please make sure you don't multiply the top by 2 and the bottom by 2, because this is 2 over 1. All right, so now we have the area. We need to now take the derivative of it, because we're trying to find the minimum, the radius that would give us the minimum material. So a prime of r is going to equal 4 pi r, and then the derivative of this is just negative 2,000 over r squared. All right, so now we're going to get a common denominator. So we're going to multiply top and bottom by r, so that gives us 4 pi r squared minus 2,000 over r squared. So now we're going to say, okay, what would make the derivative undefined? Well, r equals 0, but that doesn't make sense to have a can with a radius of 0. So then we're now going to take the top and set it equal to 0. So 4 pi r squared equals 2,000. And we're going to divide by 4 pi, so r squared is equal to 500 over pi. So r is equal to the square root of 500 over pi. Correction actually here, I need to multiply top and bottom by r squared to get a common denominator. So let me just go back here. This should be r cubed, and that should be r cubed. That should be r cubed, and that should be the cube root of 500 over pi. So sorry about that. And if you use a calculator, you'll find that to be 5.42, somewhere around there. And if you take that r and plug it into here, 1,000 divided by pi times 5.42 squared, you get a height that is approximately 10.83. Here's another tricky one. A rectangle is inscribed under one arc of the sine curve. What is the largest area the rectangle can have, and what dimensions give that area? All right, so first thing I'm going to do is I'm going to call this distance x. And because of symmetry, that distance here is also x. Now, it's something that we need to understand here is that if this is a sine curve, we need to understand that the x-intercept here is pi. All right, so that would make this distance here to be pi minus 2x. So this distance I'm going to put in yellow is going to be pi, which is the whole distance, minus 2x. So this is going to be pi, you write this out here, pi minus 2x. Now this is just simply going to be y. We'll call that y. So this point P, obviously we'll call some point x, y. But remember, x is not the length of the rectangle. X is the distance from the origin over, and y is the distance up from the x-axis. So in order to get the area of this rectangle, we have to write, well, the length of it, which is pi minus 2x, times the height, which is y, but y is sine of x, so sine of x. Now that right there is the hardest part to the problem right there, is getting that. Now we have to take the derivative. So a prime of x, by way of product rule, is going to be the first, which is pi minus 2x, times the derivative of sine, which is cosine of x, plus the second, which is sine of x, times the derivative of the pi minus 2x, which is negative 2. All right, so now we have a prime of x is going to equal pi cosine x minus 2x cosine x minus 2 sine x. All right, so we need to take that and set it equal to 0. So at this point, we're going to use a calculator because the only way you can get this answer is if you use a calculator. So if you use a calculator, you will get, either by plugging it into the solver or graphically, you'll get x to be 0.71. Make sure your calculator is in radians. Now, many students will put that down as the length of their rectangle, but it's not. That's just x. That's the distance away. Now, sine of x is the y, and that's going to be sine of 0.71, which is approximately 0.65. All right, so we know that our y is 0.65, but to get our x, we have to do pi, not our x, but our length, should I say. The length is going to be pi minus 2 times 0.71, which I believe is about 1.72. So this is going to be a 1.72 rectangle by a 0.65 rectangle. And that's going to give us the dimensions of the largest rectangle that we can fit under one arc of the sine curve. All right, example 7, moving along, a figure is shown here. And what we want to do is we want to find the volume in terms of x and y of the cone. So we will use the equation volume is equal to 1/3 pi r squared h. So we'll say volume is equal to 1/3 pi. R is the radius of the cone, that's x, so x squared. And the height of the cone is y plus 3. And that is our volume in terms of x and y. So now part B, we're going to write the equation of the volume of the cone only in terms of x. So that means we need some equation that relates x with y. Well, we have a nice convenient right triangle here, so we're going to do the Pythagorean theorem. So we'll say x squared plus y squared equals 9. And so y will be equal to the square root of 9 minus x squared. So now we'll go ahead and plug that in. So the volume is going to equal 1/3 pi x squared, and then y is going to be the square root of 9 minus x squared plus 3. And we can rewrite that a little bit. We're going to distribute the 1/3 pi x squared in there, so that will give us 1/3 pi x squared square root of 9 minus x squared, and then plus the 1/3 and the 3 are going to cancel, leaving us with pi x squared. Okay, now we want to find in part C the volume of the largest cone that can be inscribed in this sphere. So we want to take the derivative of this volume that we found in part B. So this is going to be a little tedious here, but v prime of x is going to be, we're going to use the product rule. So we're going to take the first function, 1/3 pi x squared, times the derivative of this. We've seen this 100 times, so that's going to be chain rule. So that's going to be 1/2. Leave the 9 minus x squared alone. Drop the power down to negative 1/2. And then multiply by the derivative of 9 minus x squared, which is negative 2x, plus the second function, which is the square root of 9 minus x squared, times the derivative of 1/3 pi x squared, which is going to be 2/3 pi x. All right, now we're going to take the derivative of pi x squared, so that's going to be 2 pi x. All right, we can do a little bit of simplification here. The 2 can cancel out there, and we can move this to the bottom. So this is going to be negative x times x cubed. So that's going to give us a negative pi x cubed over 3 times the square root of 9 minus x squared plus the square root of 9 minus x squared times 2/3 pi. So it's going to be, we'll just put the 2 pi right here, over 3 plus 2 pi x. Now, once again, this is a calculator problem. So you can go ahead and stop your algebraic handwritten work here, plug this all into a calculator, and you'll see that x is approximately 2.83. All right, so if you plug that into your volume equation, you will get a maximum volume of 33.51 units cubed. Okay, last example, a manufacturer wants to design an open box having a square base with a surface area of 108 square inches. What dimensions will produce a box with maximum volume? So let me underline what we are trying to maximize in this problem. We're trying to maximize the volume. All right, so we have the surface area. So let's just write down the volume actually. Let's write down the volume. We are trying to maximize. So the volume of this box is going to be length times width times height. So it's going to be x squared h. Now obviously we have two variables, so we got to get rid of one of them. So we're going to use our surface area in order to figure out how to write an equation that relates x and h. So we have 4 equal sides, and they all have an area of xh, front and back, right and left. So the surface area is going to be 4xh, and then the area of the bottom is just x squared. And remember that there is no top. All right, so that's going to be equal to a surface area of 108. All right, 4xh plus x squared. So let's go ahead and solve this for h here. So 1/8 minus x squared equals 4xh. And then we're going to divide by 4x, and that cancels. So our h is going to be, and I'm going to go ahead and divide this out. That's going to be 27 over x, and that's going to be minus x over 4. All right, and so now we can go ahead and take that as our height and plug it into here. So our volume in terms of x is going to be x squared times our height, which is 27 over x minus x over 4. And we can go ahead and distribute this in. So v of x is equal to one of these x's cancels with one of these x's. So that's going to be 27x minus x cubed over 4. Now we're going to go ahead and take the derivative. So v prime is equal to the derivative of 27x is 27. The derivative of this is going to be 3x squared over 4. And we're going to set that equal to 0. So that's going to be 27 over 1 is equal to 3x squared over 4. 4 times 27 is 108. So 3x squared is equal to 108. We're going to divide by 3. So we get an x squared is equal to 36. x is equal to technically plus or minus 6, but you can't have a negative thickness of a box, so x equals 6. All right, so if x equals 6, that means this is 6, and then we can find our height by plugging in 6 here. All right, so let's go ahead and do that. Well, I'll tell you what, let's just plug it in here. So 108 minus 6 squared, that's going to be 108 minus 36 over 4 times 6, which is 24. So 108 minus 36 is 72, divided by 24 is 3. So my dimensions are going to be 6 by 6 by 3, and that is going to be the way that you can get an open-topped box with maximum volume.